Okay, good afternoon. Two administrative things. One of them on the board over there, we're interchanging the lecture topics for Wednesday and Friday. We're going to do the lazy evaluator first, analyzing evaluator second. This is an experiment. The reason for it is the TAs all think that there's more to talk about in discussion section about the lazy evaluator, so they want you to have that lecture before discussion section. So don't get confused. Secondly, we're getting in toward the end of the semester. So it's important not to be late about things at this point because your readers are also students and they have their own end of semester crunch the same as you do. And it really makes things a lot harder if things get in late. And in particular, the grading complaint deadlines are speeding up. So there are grading complaint deadlines that are in the first day handout and also in Course Reader Volume 1 right at the beginning. And you'll see that there's like 3 of them almost on top of each other. And just a reminder, you're complaining about both missing grades and grades that you think are incorrect. So don't, if you have a missing grade, don't wait for it to show up before you complain, because you'll miss the grading complaint deadline, and we don't want that. If we have a problem about grades, we'd like to know about it in a timely manner so we can try to fix it. Okay, that's it for administrative things. Back to MapReduce. So these are the same pictures that were on the board last time. And again, remember that F1 is called F1 because it happens first and because it takes one argument. So the mapper function takes in a key value pair, a single key value pair as its argument, and it returns a list of key value pairs that could be empty or could have one thing in it or could have 20 things in it. The reducer, F2, comes second. It's a 2-argument function. It takes an accumulated so far value and a new value and combines those to produce a new value so far. So the one important difference that you can easily get tripped up on is that the mapper function gets a complete key value pair as input. The reducer function just gets a value. And the reason for that is very often we're going to use some simple function like plus as the reducer, and that wouldn't work if we had key value pairs. So the reducer never knows what key corresponds to these values, and it shouldn't have to know. The reducer function should be associative. For those of you who missed out on high school, that means A function B, function C, should be the same as A function B function C. It's possible to have non-associative reducer functions, but then you have to start worrying about exactly what order things happen in, and it's best if you don't. Almost all the time, the reducer will be plus or times or word or sentence or list, or cons, not list, or cons stream. Okay. All data are in the form of key value pairs. We talked about that. The reason, again, for key value pairs is that sort operation in the middle, which looks at the key and doesn't look at the value to do the sorting. And so the reduction is on a per key basis. And that's why key value pairs matter in the MapReduce process. Stop me if I say something you don't understand. I'll stop that. What do you mean DHCP? Okay, does that mean this still works? Yeah, oh, look at that. What a surprise. Okay. So we're doing things in parallel. That means each processor runs its own map, and each processor runs its own reduce. That's how we get the benefits of parallelism. that we're not trying to do the entire data set in a single process. So that's just easy to forget in the scheme of things. So how do we know which values from the file go into which mapper? And the answer is it really doesn't matter. The key value pairs initially at the left end of the diagram are in no particular order, and you just get random ones, and that's okay because your mapper function, F1, is only looking at a single key value pair at a time. It doesn't do anything global with respect to the entire data set. That's the reduction stage that thinks about sort of the big picture. And each of the reduced processes is completely separate from one another. And because of that, instead of a single result, as in the simple one processor case we're accustomed to, what we get is a stream of key value pairs, where each value is the result of combining all the initial values for that key. And finally, the key that in the key value pairs that your map returns doesn't have to be the same as the key of the incoming data. So we'll see in most of the examples we do, where we're looking at text files, the key is the file name, and the value is one line of text from that file in what comes in. And most of the time, we just ignore the file name, which is the initial key, and we make up new keys, which are the individual words or something like that. Okay, and the reason that your mapper function F1 has to return a list of key value pairs is that the map stage is also the filter stage, so sometimes you'll return an empty list, and also sometimes you'll split up an incoming line from a file into multiple key value pairs. For example, one per word, very common thing to do. Right, okay. Oh yeah, and the sorting, I've only drawn one big tall box in the picture, but the sorting is done in parallel also. It's a bucket sort. That is to say, as a mapper function outputs a key value pair, the sort piece of MapReduce sends that key value pair to the right processor for that particular key. So we get all the key value pairs for a single key together, and that becomes the input to reduce. Okay, oh, that's what I didn't put in the diagram. I knew there was something. F2 goes to all the reducers, and base, of course. Okay. All right, so since each reducer gives us only part of the result, what MapReduce returns when you call the MapReduce function is a stream of key value pairs. And it's, generally speaking, a sorted stream, sorted by key. Okay, because that's how, in the actual MapReduce, underlying MapReduce software, it's possible to specify the sorting algorithm, how you decide which key value pairs go to which processor. But that's one of the things that we kind of sweep under the rug in our simplified MapReduce interface. Okay. Questions at this point? That's all pretty abstract. Now we're going to start running code. Once we start running code, I'm hoping it'll be clearer what's going on, and maybe you'll have questions. So, SSH to iCluster, and you'll log in, I'm sorry, iCluster1 is what you can connect to, .cs, I think. Okay, that is you. Maybe it does matter. Or maybe I'm not on the net anymore. Let's find out. It's eeks. All right, eeks. Yep. And you might get a message like this. So I'll say yes. Okay, great. So you will log in with your class account, and it's the same password on iCluster 1 that it is when you log in the lab. STK. Okay. Oh yeah. I didn't talk really about the last argument to MapReduce. So F1 is your mapper function. F2 is your combiner function for the reduction. Base is the base case that the reduce starts with. And then instead of a list of data, as in the simple example on the left, there are actually two things that can be used as that last argument to MapReduce. One is, in quotation marks, a file name on the distributed file system of iCluster, which is a cluster of several machines. So that's one thing you can do. And the other thing you can do is use the result from a previous MapReduce, which is a stream of key-value pairs. So if you say define foo to be MapReduce blah, 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 then later on you can say MapReduce F1, F2 base foo. Okay? And some of the problems that you're going to be doing in the lab require you to do that there's two passes through MapReduce before you actually get the answer you wanted in the first place. Okay, so let me actually start with the very simplest possible example and see if this works. I'd like to just look at what's in a file on the distributed file system. So I'm going to try to use a MapReduce that essentially does nothing. Okay? It just passes all the inputs on. So, so here's a good pop quiz. If I just want to pass all the data through, what should I use as F1? Yeah. The identity function, lambda XX. Agree, disagree? Yep, you're all wrong. Okay, everybody whose thumbs up is wrong. Because F1 has to return a list of key-value pairs. So in this case, it's going to be a list of length 1. I'm just going to say list. Because if you call list with one argument, it does what we want here. Okay, so that's a little tricky thing to remember. What am I going to use for the combiner? I'm going to use cons stream, because I want to get a stream out. I'm going to say the empty stream. This is kind of a hack. Cons stream actually, in truth, is treated specially by MapReduce. It notices that you said cons stream, and it treats it as a special case because the sort of natural way to do an accumulation is right to left. And you can't exactly do that for infinite streams. So it has to go left to right to come out right. No? Jordy's making faces at me. What? Oh, you think this isn't going to work? No. It does. Oh, maybe. You think it goes all the way to the end. Well, we'll see. Well, maybe we won't see. I'm not quite sure how to find out, except by having a function that prints something here, the way they do in the book when they introduced streams in the first place. I wanted to show you how it works. Okay, so I'm going to put in a file name, /Gutenberg /Shakespeare. This is actually not the name of a file, it's the name of a file directory, and there's a file per Shakespeare play in it. It says Gutenberg, by the way, because this data comes from something you ought to know about called Project Gutenberg, which is an effort to get every public domain major work of literature online. It's a volunteer effort. People scan in books and fix the mistakes that the OCR made and make text out of it. So, what you're about to learn, I hope, the only thing bad you're about to learn, is that the disadvantage of our MapReduce implementation is that there's a very large setup time. So this is a MapReduce that's doing nothing, basically. There's no computation involved. When I start it, it says working. By the way, okay. So that took about half a minute. So that half a minute was almost entirely startup time. Now the sad thing is that you can't really see the data here because of these promises. Oh, it looks like, doesn't it, that this is that in the key value pairs, the key is a name of a play or poem or something, and the value is a stream of lines of text from the file. So I would like to say show stream Sorry? Oh, okay. Oh, yeah. Good point. But I still have to map showstream over these things to get the text. So lambda of key value pair no, I just map, wait, I'm sorry. Map showstream over get last MapReduce output. And that's in case you ran a MapReduce and it took a long time and you forgot to save the result. So let's see what this does. What? Oh, whoops. Yeah, okay, thank you. Stream map, show stream, over, get, last, whoops, MapReduce output, close, close, close. All right, well, no, we still have some, I wonder why that didn't work. Yeah. Well, anyway, it doesn't matter. Okay, so what we're looking at here, of course, oh, that's right. So we have a stream of reductions by play. So this thing that says A Midsummer's Night's Dream dot promise, that promise is a stream of all the lines. So I probably mean 3 levels: stream map, show stream of stream map of show stream of stream map of show stream of thing would probably work, but I'm not going to try it. I just wanted to let you know that you can get to the files out there, and that this is what a kind of not really doing anything MapReduce call would look like. It would be list as the F1, and it would be constream as the F2. I could have just said cons, and then I would have gotten lists, and then it would all be visible, but it would be a lot of lists, because one Shakespeare play has like thousands of lines. So I really wouldn't want to go through them all just to prove to you that that file is out there. Okay. All right. Actually, what I really wanted to do, let's see if I can do this. Of course not. Yeah. Okay, well, this is bad. I didn't really want to load it. Okay, we'll see what happens. But what we're doing, yeah, no, this is bad. Let's stop this. Wah. How do you stop a... Okay. There we go. Government buffer has no process. Okay, let's try again. Okay, so here's word count mapper. Word count mapper takes a key value pair whose key is a name and whose value is the text. So what I want to do, I've taken here a very small file called Beatles songs, and I'm going to find out how many times each word appears. It's the same thing that I did last time on a single processor, but now we're doing it in MapReduce. So word count mapper looks at KV value of an incoming key value pair, and it maps over that lambda of word make key value pair word 1. So A1, hard 1, days 1, night 1, all right? Like that. And then we call MapReduce. Word count mapper is the F1, and just plus is the F2 with a base case of 0. So now, if I, oops, hey, what is this? Control, here, I'm just going to do it the easy way. There. Okay. Hello? Oh, whoops, return. All right, so here we go. MapReduce in progress, working, blah, blah, blah. And this is a really short file, so it's going to take the same 30 seconds or so that the other one took. So this MapReduce interface is a work in progress, and oh, that's pretty good. That was way less than a minute. That was like a quarter of a minute. It takes a while to start up because it has to send your environment out to all the worker machines before it really starts doing anything. So let's go ahead and show stream word counts. So if this doesn't look like a sorted list, it's because our idea of a word on a line is anything with spaces in between. So this is the word open parenthesis go, which comes from the song Anna, parenthesis, go to him, close parenthesis. This is, Sgt. Pepper's Lonely Hearts Club Band, reprise. Right? This is she's, no. What song is this? She's So Heavy. What's the real name? Yeah. Okay, anyway. So here we finally get to A, which occurs 17 times. There's one across, that's across the universe. Act, naturally. After, one after 909. All, there's lots of those. There's all you need is love and all my loving and Anyway, am, only one of those. That's interesting. I am, I said, must be. Anyway. Okay, so that's word counts. And now, oh yeah, so here's the example that I did before on Beatles songs. Okay, so find the most commonly used word. Okay, so here we go. And while it's working, let me back, whoops. Here's mapper and reducer. The mapper says, it says something very strange. It says, make KV pair first of KV key KV pair, KV pair. All right, so that's a really strange thing to do. Why are we doing this? So we have, for example, a key value pair that says okay, so the album is with the Beatles. Is that right? Wait. First of KV, key of KV pair. Oh, it's on word count. Never mind. You're right. Thank you. Starting over. Okay, so we've done word counts already. We're not looking at the raw data. So we have something like what was it that there were 7 of? All. Yeah. Okay, so we have something like this. And now what we're doing is we're using that whole thing as the value for a key value pair whose key is A, the first letter of all. So that's what this says to do. That sounds like a weird thing to do, right? Why on earth would we want to do that? Well, think about the reduction. We want to find out what's the most common word altogether. We'd like to do that somewhat in parallel, right? We don't want to have just a single reduction because there's a bazillion words, and that would be a bottleneck. So we want all these computers reducing separately. But it doesn't do any good. It's a little bit like in concurrency control where you have to pick exactly the right granularity of what to put in a critical section. There's no critical sections here. It's all functional. But there's this same kind of granularity issue. We have somewhere on the order of 10 computers to work with. If we have a process per individual word, all we're going to find out is that the most frequently used word in the word all is the word all. So the parallel reduction wouldn't be helpful. On the other hand, if we just merge everything together, then we're only using one of our 10 processors to do the reduction. So the compromise that I used is to say, okay, let's divide this into order of 26 subproblems. So an A problem and a B problem and a C problem and so on. So we'll find the most common word that starts with A, and then another reduce process will find the most common word that starts with B, and so on. Okay? So when we do that, show stream frequent, we get this. The most common word that starts with open parenthesis is reprise. Oh, if there are ties, we just get one of them. It doesn't matter. The most frequent word that starts with 1 is 1. Most frequent word that starts with, it is? Where's there a 1? Oh, yeah, the 1 after 909. The most frequent word that starts with 9 is revolution number 9, 9. The most frequent word that starts with A is A. So far you might be forgiven for thinking that this and this are always the same, but the most common word that starts with the letter B isn't the letter B, it's the word BE. The most common word for C is cry, occurs 3 times. Cry baby cry is 2 of them, and I don't know what the third one is. I'll cry instead. Ha. The most common word for D is do, love me do. But anyway, sorry. Okay, so and so on up to Z. Now, at this point, we have a stream that's really short. Even if there's 20,000 English words, there wouldn't be in the names of Beatles songs. But let's say we were doing this, as you will in lab, for the works of Shakespeare, and there are, on the order of tens of thousands of different words probably in Shakespeare. By the time we've done this parallel step, we're down to 26, modulo a couple of punctuation things. So now we can do a single processor reduction and get the answer. But we haven't yet talked about how the reducer works. We talked about what the mapper does. It makes things that look like this. So what does the reducer do? And here's the tricky part. Remember I said that the reducer doesn't see the key, it only sees the value, right? But the way I've set things up here, the value of this yellow key-value pair is the white key-value pair. So the value that the reducer sees is the original key-value pair that we started with. So therefore, in the reducer function, this is the function f2, find MapReducer, current and so far are key-value pairs. And we compare the two values. If current is greater, we pick current. Otherwise, we pick so far. So in the case of ties, it's whichever one we saw first. OK? So that gave us frequent. And now, I'm going to take the result of that. I'm going to stream map KV value frequent. So that gets rid of these letters that I don't really care about. So we're turning the nested key value pairs into just plain ordinary key value pairs. And then we use find max reducer to find the most frequently used word. And the base case value is this fake key value pair in which the value is 0. And that is never going to happen in any of the ones that really are in the stream frequent, because if a word appears 0 times, we aren't going to see it at all. But that's what we use as our starting value for the reduction. And it turns out that the most frequently occurring word is you at 22 times. When we did it on Friday with just the first 3 albums, you'll recall the most frequently occurring word was I, not you. So what that says, I guess, is that the Beatles got less self-centered as time went on. See, you can learn interesting things by doing this stuff. OK. OK. So I would like to find the total number of lines of text in all of Shakespeare. OK? So let's start this running. And while it's running, we'll say, OK, the reducer, that's straightforward. That's just plus. The mapper takes a key-value pair, returns a single key-value pair in which the key is the word line, and the value is 1. So for each line of text in Shakespeare, we're returning exactly the same key-value pair. So all the reduction is being done in parallel now. So we turned every line of Shakespeare into a single key-value pair. Now if I look at Will, if I say, actually I can say show stream Will, and you'll see that it's a stream of length 1 because there's only one key, so it all got reduced. The total number of lines of text in Shakespeare, according to Project Gutenberg, is 112,251. Okay? So that's what you're aspiring to if you want to be an important English writer. Okay. One of the things you're going to do for us is modify this example so that it tells us how many lines are in each Shakespeare play. And this is the result that we want. This is in the lecture notes. So you can try out your program to see if you got the right answer by seeing if your answer agrees with our answer. So each Shakespeare play is on the order of 2,000 or 3,000 lines of text, looks like. Okay? So what are you going to take away from this lecture? After all these examples turn into a blur. I'm not spending a long time on each one because they're in the lecture notes, so you can go back and look at it at your leisure. I'd like you to take away a couple of things. One is that without very much trouble at all, we can do useful parallel computation for a fairly wide range of problems. And again, as I told you last time, not every problem lends itself to this kind of easy data parallelism. Some things you have to work a little harder at, or a lot harder at. But a lot of things do lend themselves to data parallelism, and we're looking at some examples. And for those ones, using the MapReduce mechanism does what abstraction is supposed to do. Remember, this whole course is about abstraction. Abstraction basically is a process of enabling you to think in terms of the problem you're trying to solve rather than thinking in terms of the limitations of computer hardware, right? So in terms of computer hardware, below the abstraction barrier of MapReduce, we have to think about the fact that computers sometimes fail. We have to think about the fact that these files are actually distributed over several different computers. We have to get the data from the computer that has it to the computer that needs it. We have to think about exactly what basis the sorting is done. We have to think about all of these different things. We have to think about the construction of streams out of the results. Because, Hadoop, the MapReduce implementation that underlies this, doesn't know about streams. It knows about just iteration and emitting one value at a time. And we have to turn that process into something that looks like the kind of stream that we've been working with. So all of that stuff is swept under the rug of this very, very complicated to implement but simple to use abstraction. So that's point number one. Point number two is how to master this key-value pair business so that you know whether you're thinking about a key-value pair or you're thinking about a list of key-value pairs. Somebody should make up a good name for that, comparable to forest, but I haven't thought of one. Sorry? Not an associate? No. That's I'm sorry, not a list of any old key-value pairs, a list of MapReduce key-value pairs. So it's a little different from an association list, but yeah, kind of. It is that idea. When you're thinking about just a value, okay? So you have to keep that straight in your head, including screwy cases like this, where the value from one point of view is a key-value pair from another point of view. What this should remind you of is the implementation of two-dimensional tables, right? It's got nothing to do with two-value tables, but there's this situation where you look at something from above it in the data structure, it looks like a value in a key-value pair. And when you look at it from underneath, it looks like a whole one-dimensional table, right? Remember that? This is the same kind of thing. If you're looking at it from the yellow point of view, this thing down here is a value, but from the white point of view, it's a key-value pair. Okay? So those are the big sort of takeaway points. And then just looking at the details of this, seeing how we did it. And that's about it. Boy, I talked fast today. Okay, questions? Yes?
When you're calculating all the lines in all of Shakespeare, you said it reduces it in parallel, but since there's only one key, wouldn't it just be...
Yeah. No, in that example, it doesn't reduce in parallel. So he's asking about finding all of the lines in all of Shakespeare. And in that case, since I use the same key for everything, it is going to be just one reduce process. So one of the things that you want to do is make that more efficient, which we could do by the same trick I used here about the first letter and so on, that kind of thing. Okay, so thinking about how to make something efficient is, part of what you ought to be doing. This is kind of a deliberately bad but simple example for you to build on. Is that a hand up, or are you just fidgeting? No. Okay, other questions? Yeah? Where do we implement the breaking it up into the looking at the first letter? Okay, that would be right here. So I'm making a key-value pair whose key is the first letter of the key of the original key-value pair. Right? So the key value, the key of the original key-value pair in this example was the word all. First of all is A, right? Not first of all, but first applied to all is A. So that's the key of my new key-value pair. The value of my new key-value pair is the entire original key-value pair. Okay? So that's how that works. Yeah?
When you put in the input file, it's just a normal file. But for you to pass it into F1, you have to make it into a bunch of key-value pairs.
Okay, no. The question is about the original input file data and how that becomes key-value pairs. The file that you're working with, so this Gutenberg/Shakespeare thing, is not just a bunch of text. It's already been kind of Lispified so that it has key and value by the time you see it. And that's part of the implementation of MapReduce, is that when you call it with a string as the last argument, so it's a file name, it says, oh, okay, this is a file name. I'm going to take this file, and I'm going to make a stream of key-value pairs whose key is the file name and whose value is one line at a time of text. Okay? So that, again, that's another thing that's sort of swept under the rug here. But you're right to ask about that, because if you look at the Google MapReduce paper, they have different formats of keys and values for different situations, and that's one of the things you have to kind of work out. Okay? Yeah? Okay, so how do we compare in the reducer? How do we do the comparison? Well, we're doing a greater than of the KV values, not of the entire thing. So remember, again, current and so far are yellow values, which is to say white key value pairs. So that's how come we can take key value of it. KV value, I mean, of it, which is this 7. So what we're comparing is this 7 with some other number for some other word. Does that answer your question? What the reducer sees, so if you look at the picture, this is going to be the letter A. And then each of these values is going to be, you know, all .7 and A .23 and whatever, okay? For the different words that start with A. Any questions? Oh, try to remember to try to keep in your mind a distinction between how MapReduce works and how my particular example works. Okay, so that business about the first letter, that's not built into MapReduce. I could have done it in better ways. If I were really, really serious about parallelism, if I were Google dealing with all the data in the world, I would notice that assigning each letter of the alphabet to a processor means that the one that gets Z is not going to work as hard as the one that gets A. Right? There aren't very many words that start with Z. So I would say, well, maybe that's not such a good way to do it. Maybe I should have, you know, 3 processors for the letter A, but I should have one processor that's doing, you know, UVWXYZ altogether. So that's the kind of thing that, you know, we're trying to simplify your life by not being absolutely as parallel as we possibly can, but on the other hand, not being not parallel at all either. Okay? Other questions? No questions. Okay. I hope that means that you're all happy about this. So, oh yeah, one just final word about this whole thing, and I said it Friday, but can't say it too often. This MapReduce, this is a function. Okay, so we're taking parallelism and doing it in a way that's functional, which means there's absolutely no danger of these different processors stepping on each other's toes. So that whole business about critical sections doesn't apply to the user of MapReduce. The implementation of MapReduce is not the least bit functional. It's full of what's the state of this machine and this process and all of that stuff. So there's a lot going on under the surface that's not functional, but it's done in such a way as to present you with something that is functional, and that vastly simplifies the use of parallelism. And that's why MapReduce, you know, is such a good tool. Okay, see you Wednesday.